TRAPPIST-1. From the moment of its discovery, astronomers knew they had found something incredibly special. 7 Earth-sized worlds orbiting around a red dwarf star, several of which were within the habitable zone. It was closer, brighter, easier to distinguish these planets than any others that had been seen before, and immediately went right to the top of the list of the most intriguing and interesting places to search for atmospheres around exoplanets and potentially signs of conditions that could be habitable. And incredibly, this is the kind of planetary system that is observable by the James Webb Space Telescope. And this is one of the goals of the James Webb Space Telescope, is to understand the atmospheres of exoplanets. So it's not a surprise that a significant amount of time was put to observing the TRAPPIST-1 system. But here we are, more than 2 years since James Webb began operations. Many observations have been made of the TRAPPIST-1 system, and yet we don't have a satisfying answer to what those planets are like. And I get so many questions from my audience about this. And so today, I'm going to bring you answers. My guest is Dr. Julien de Wit. He is a professor of planetary science at MIT and works with the Disruptive Planets Group. He and his team have developed a roadmap, a way to comprehensively study the atmospheres of the TRAPPIST-1 system, as well as other planets orbiting around red dwarf stars, to, in a very efficient manner, build up a ladder of understanding to get to the point where we can know once and for all, are these the kinds of planets that could potentially host life? So enjoy this fascinating conversation with Julien de Wit. If you want to know what's happening with TRAPPIST-1, this is the interview. You're going to find out the answer. All right, enjoy the interview. Julien, what was it like when you first looked at the spectral data from JWST at the atmosphere of an exoplanet compared to your experience in seeing it with Spitzer, other telescopes?
Yeah, so the experience was that it was so obvious that we just enter a new era. In terms of data science, not only the number of points that we have per wavelength bin or per color point, if you'd like, but also the precision was just incredible. So it was clear to us that what we'll be able to say about these planets and their stars also will be well beyond what we have done before.
I mean, I think about, we see the press releases coming from NASA and from other scientists saying the presence of carbon dioxide and carbon monoxide and methane and water vapor and all these kinds of things in the atmosphere of an exoplanet. From someone who looks at the data and sort of thinks about the confidence levels and the, how certain does this stuff all feel to you now?
Yeah, so the detections of molecules have, for most of what we've done, been very solid, even before James Webb, right? Detecting molecular features is quite an easy thing to do. However, the challenge that we started to face is associated this feature that we're detecting with a number density, like how much of that molecule really is there, and that is a bit challenging. But in terms of detecting CO2, detecting SO2 and so forth, these molecules are there, and these are molecules that were otherwise, out of reach. So now with James Webb, we can easily detect this molecule, and that's exciting.
So I guess that's kind of two parts. So that with James Webb now, there are molecules that were previously out of reach that are now within reach. You said sulfur oxide. What are some other examples of the molecules that are now in reach and maybe hopefully will be in reach with James Webb?
Wow, that's a great question I did not prepare for, but a lot of them. The reason is simple. Most of the spectral analysis we were doing before were in the wavelength range with Hubble Space Telescope between, say, 1.1 to 1.7 micron. And now with JWST, and there's shorter wavelengths we could do with HST, but now with JWST, we're really going much further into the near infrared, which allows us to really detect molecules because that's where they vibrate, that's where they interact the most with light. And so one that's just coming to mind on top of the ones you'd already mentioned, CO2, SO2, is, for example, ozone, which is such a cool molecule that also absorb around 5 micron. But there's a bunch of molecule happening to absorb light in that wavelength range. So as we're going further and further into the infrared with a big telescope, we can do atmospheric analysis and reveal a wide range of molecules that were otherwise inaccessible.
And so part of the limit is the wavelength. So Hubble, near infrared, but as you say, it only goes into a couple of microns. It doesn't go all the way deep into near infrared the way James Webb, but also just the size. Webb is 7 times bigger than Hubble. It's a monster. The clarity that you get in those wavelengths that you could never observe with a large telescope before, these all come online now.
Exactly.
So I want to talk about the TRAPPIST system because I just get so many questions from my audience about what is the state of the planets around TRAPPIST-1. So I'm just going to pass that question on to you. I mean, we're all pretty familiar that the first 2 planets, B and C, have been rendered airless thanks to Webb. But what do we know so far about the system? What is the state of TRAPPIST-1?
Is that okay if I start challenging that first assessment of the inner planets?
Oh, yeah.
Okay.
That's great. Please challenge it.
Okay.
That's
Let's start with
exciting.
that. Let's start with that.
Okay.
So what has been done for the inner planets, what has been published for the inner 2 planets, is that the one emission photometric points, or actually 2, depending on which planet we're looking at, suggests that they would be airless. But because it's not a spectral analysis, but rather 2 points at 2 different wavelengths, there's not much information really that can be extracted from that. And since this paper that you're referring to, claiming that this could be associated to the lack of atmosphere, have been pushed out, other papers have followed up by showing that there's actually a wide range of atmospheric models that could still be consistent with the data observed. So in other words, the assessment that they are airless has not been conclusive. Other programs have been going on, and there are papers currently being worked on that push the analysis further, notably by getting a full phase curve. So what has been done so far, to put this further into context, and I'm sure your audience knows about that, but still, it's been looking at the brightness temperature of the planet, so how hot a planet is, by looking at the flux drop when the planet passed behind its star. Okay. Now, if the planet was without an atmosphere, you would expect the day side to be quite hot because there would be no atmosphere moving heat from the day side to the night side. Okay. And so the experiment that was done is, let's look at different wavelength, photometric band, so there's no spectral analysis there, and let's see how hot the planet is. And if it is hotter than what we would usually expect if there's an atmosphere, then we can come to the conclusion that there is no atmosphere. But it can be more complex. There can be situations where you can still have a hot day side while having an atmosphere. And so a big program that has been ongoing, or that a big observation that was done earlier this year, was to look at a whole phase curve of the planet, so that then you can actually talk about heat redistribution, right? Because you have information about the day side during the eclipse, but as the planet turns around its star and you monitor the whole flux coming from the system, then you can talk about what's going on also closer to the night side. And so these studies are actually going to help us bring this to an end, bring this to closure, because they are going to tell us what's going on with B and C. So that's for B and C. Should we turn to the rest of the system?
Well, I want to just make sure I totally understand that. So is it really just like in that first round of observations, the people making those observations, whoever had booked the time with Webb, had as much time as they could get, and you didn't get a conclusive answer out of a short amount of observations. And so now, to do another round with a longer observation, you should be able to get to a conclusive answer. So
yeah, exactly. Yeah,
okay.
It's basically we're building the plane as we try to fly, and it's understandable, right? So step by step. We a few years ago we thought that just getting the eclipse would be sufficient to tell us if there's an atmosphere, and now that we have the data and we try this really complex, global circulation model to try to get a sense, okay, is it actually certain that it means no atmosphere? We realize actually no, it's a bit more complex than that, and so we have to go back and ask for more observations so that we can keep on fine-tuning the analysis and disentangling with more and more certainty.
Yeah. Analogy I like to think of is back when the Soviets were exploring Venus with the Venera program, they didn't know how bad the atmosphere was. And so they just had to send probe after probe, building it stronger and stronger. and it would, it could only reach a certain depth and they would lose contact with it. And finally, after they really truly appreciated how difficult this process was, and they were able to get some images from the surface. And so it's like, you think you're going to get what you need because the time is so precious on Webb. To ask for any time, it's a big ask.
Yep.
And so I'm sure they're like, what's the minimum amount of time that you need to get to do the science?
If you'd like, we can really talk about this difference so we can be quantitative, right? An eclipse takes about 5 hours. And you need a few of them to be able to build up the signal-to-noise ratio, the scientific confidence, right? A phase curve is about 70 hours, right? So it is indeed a much bigger ask to get to that point. And so you're right, it's really a matter of time. Like the key resource that's limited here is time. And so you do the minimum ask to move one step forward, and then you see where you're at. And then if you need to move another step, you might need something bigger. And that's the whole point, the whole idea behind the roadmap is to really piecemeal everything that needs to be done, but what allows for key deliverable so that we can sit, assess where we're at, and then plan the next step. And so it's really the idea behind the roadmap.
And are those the actual numbers? Like, it was 5 hours to make that first observation of TRAPPIST-1b, and now it looks like it's going to need 70 hours, or is that just like a?
Yeah, these are the numbers. So multiple. So
those are the numbers.
One,
yeah. Okay.
So for TRAPPIST-1, one eclipse or one transit takes about 5 hours, and then you have for TRAPPIST-1b, I think 4 or 5 eclipses were obtained to get to that first paper, but then the full rotation curve is about 70 hours. So that gives you an idea of how much time has to be spent, and the phase curve has been observed. So it's something that actually has happened.
That 70-hour observation has been made?
Yeah, it has been made. Mm-hmm.
And is it still in embargo right now, the results?
Definitely.
Okay. All right. Yeah, I mean, that's a big ask to get 70 hours on Webb. I know I've talked to many scientists, and they talk about the productivity of it in just an hour. And to say, well, we need it for 70 hours, please, for one planet in a system. Yeah, I can see why you'd take these steps tentatively. That's great. I mean, this is the most satisfying answer that I've had in sort of going down this journey.
If you really think about it and really unpack the core missions or the core goals of James Webb, there are 4 of them, and one of them relates to origins of life, right? And TRAPPIST-1, by far, is the only system we have right now that can help us, or hope to answer somewhat questions related to that theme beyond the solar system, beyond the edge of the solar system, right? There's no planetary system like it. And there's no, you can go to the roadmap and look at the first figure. It shows how TRAPPIST-1 is well beyond any other system. So it is the only system we can hope to leverage to try to provide a sense of success to James Webb's 4th core mission that relates to the origins of life. So it isn't that much when we think that thousands of hours are given each cycle to different programs. So if 25% of the goals of James Webb relate to that, then 25% of these 5,000 hours could be invested in that theme, at least, and significant fraction of that should go to TRAPPIST-1. So it's not that much.
Right, of course. Is the same story for the next one, C?
B and C, I would just put them in the same package. In fact, the observation that was made, the phase curve, is an observation that's made when B and C have eclipsed at the same time. So we have a joint phase curve of the 2 of them. So the idea was to leverage the 2 of them so that we can at once constrain their properties. And I'm sure you'll hear about the outcome in the coming months.
When were those observations made?
The observations were made at the end of 2023.
Right. So I'm just checking my watch, thinking about the embargo time. So we've got a few more months left. Okay. All right, let's move on. Let's talk about D. Oh, sorry. Yeah, D.
Sure. Yeah. So D is special in the sense that it's a small planet, and you could technically do an assessment of its atmosphere with only 2 transits. So 2 transits observation, if they are done well and you're not dealing with stellar contamination, something I'm going to talk about later, you should be able to do it. And as a result, people pitched for that. So observations were taken, but still not published. And you'll see that there's a pattern there, right? For most of the planets, but B and C, There's still no paper out there. And that relates to the fact that we simply underestimated or did not account for the effect of stellar contamination when we pitched our programs. And so, I don't want to say that we have overpromised and underdelivered as a community, but there is a bit of that. I think programs went through without accounting for the most recent knowledge of what could be limitations, and now we're paying the price for it to some extent.
So let's talk about this problem then. When you say stellar contamination, what are you talking about?
Great. So remember, I've talked about this like half-rotten apple being a star and a planet passing behind it. Well, when the planet passes in front of the star, it's a transit. And when that happens, there's a small fraction of the stellar light that goes through the planetary atmosphere. For a long time, most of the community thought, and I've appreciated the fact that there was information about the planetary atmosphere there, and we called it a transmission spectrum. But that was misleading because there's also information about the star in that spectrum. So it's not just a spectrum in transmission, there's more to it. Why? Because when the planet masks part of the star, it's masking a part of the star that's not necessarily with the same emission spectrum as the whole star. And when we do exoplanetary science, we use relative measurements. We look at what's going on outside the transits and use that as a reference for what will be inside transit. But if the out of transit, so the hemisphere average spectrum of the star, is not exactly the same than the core that the planet is masking, there will be contamination. There will be information from the star bleeding into that transmission spectrum, which means we have to find tricks to disentangle between the signal from the planet and the signal from the star. And that's where we're facing a new bottleneck.
Right. And is that just an issue of understanding the dynamics between the star and the planet, or is it just more time?
It's really understanding stars better. It's really an issue with how much we know about stars. And we know quite a lot. It's just that now we need to know much better if we want to do, optimal science with James Webb.
So what's the tool to learn more about stars? Is it Webb, or are there other instruments out there that can help us understand?
That's a fantastic question. I'll have to say humbly that this is something we're still, reflecting upon. As we speak, we're building strategies, we're testing them, and we think of new instruments. There's different approach that needs to be taken in parallel because we need to try them now so that they can pay off as soon as possible, so we can implement them while James Webb is still, up and going. Some of them relied on upgrading our stellar models. And fortunately, the community has embraced that. And, for example, recently an ERC synergy grant, so 10 million euros, were invested in supporting efforts along that line. So we need to upgrade our models. But if we want to upgrade our models, we also need some ground truths. So because we need to provide reference to confirm that they are solid. And so in parallel, other efforts are being driven towards empirically driven or derived constraints. So it's really data driven. And that's some of the thing we do as well. So that means trying to find ways to understand the star better. So one of the strategy we've developed recently in this group is to do time-resolved spectroscopy. So if we have a star and we allow it to rotate and we study it with James Webb, for example, there is a way to identify different features on that star and derive empirically their emission spectrum. And then what we can do, back in the day when they built this library of emission spectra for stars, right? What we could do this way with Webb, we could build a library of emission spectra for faculae, for spots, for different features on stars in a way that's completely data-driven. And then we can use that to inform models. And so these are the kind of strategy we're trying to implement, understanding how models can be pushed further, how instrument like James Webb can be used, instrument from the ground at much higher resolution. So that's where the community is at, mapping out the realm of possibilities and moving forward and implementing. There's a lot of, try and learn.
Yeah, I mean, I think about how little we know about our own star, and it's right over there. But at the same time, I know a lot of telescopes, or missions like TESS, for example, are turning out to be surprisingly useful for observing not just where there are planets, but also the stars that are in that field, and are finding a lot of minor variations in stellar brightness, and are helping with astroseismology and things like that. And so I guess it's sort of needing to look that deeply into what these, how these stars operate to then be able to detangle the planets from the stars in the field of view.
Exactly.
Yeah.
Yeah.
So based on what was learned with the amount of observing time and sort of what the plan was, you said that the observation's already been done for D. Do you think that this time around enough observing time was done to get a more conclusive answer about D?
So the observations were done for some of these planets. It doesn't mean, though, that they were done in such a way that the stellar signal can be adequately removed from the planetary signal, right? It could be that there's only so much we can do with this data. And that is our main concern, and that is why we wrote that roadmap, because really we don't want people to be underwhelmed by results simply because the design may have been suboptimal. And so, and this is really why we want to provide this roadmap, so people keep in mind the long-term goal and understand that these are steps that need to be taken. And if at some point we took a wrong step, it's okay to go back to square one or wherever we were and then try another step. And I think this is probably how we might have to look at some of the cycle one observation. And as we move forward, we need to be comfortable with having to double down in order to make things work. And that's typically what we have to look at, I think. Orders of magnitude. If, say, you need 2 transits, if you don't have stellar contamination to take care of D, once you start accounting for stellar contamination, you need to significantly increase your baseline, but you also need to gather more transits to make sure that you understand at each epoch stellar contamination good enough to really get to the atmospheric signal. So it's just a different way to look at how we gather the data, considering that now there's a whole other player, which is stellar contamination, another signal that we have to understand together with what we're trying to get to, the planetary signal.
Are there other possible sources of error that you're concerned about beyond just the star itself?
Are we talking about TRAPPIST-1 or exoplanetary
Yeah, well,
science?
yeah. I mean, even just say M dwarf planets in general, trying to get some kind of ground truth about them.
Sure. M dwarf planets in general. The other big piece relates to flare, and flare is still stellar activity, right? But flares are challenging. I mean, they're great because it helps us understand the star better. It's still information.
Yeah, they're cool.
But but they are challenging because they are very time dependent. If you think about what I was talking about, stellar contamination, from the beginning of a transit to the end of a transit, the star rotates a tiny bit. It's negligible, and these spots in future evolve small, like not that much. So once we have developed a framework, either through improve models for the emission spectrum of these different features, or through a new data analysis technique, like having a whole rotation curve of the star that gives us the same thing, an emission spectrum for each of these different components. Once we've done that, it should be okay to take care of them, right? Once we've done that, it's good. But flares, they come and go in a matter of an hour or two, and so this transient behavior makes it just a bit more challenging to navigate. We will find ways to navigate, to handle them, but it's another beast to account for.
Yeah. I think about when doing astrophotography, and you take a bunch of frames, good, airplane, good, right? And you have to throw out the airplane one. As long as you took a lot of frames, then you'll get what you're looking for. And so in your case, it'll be good, flare, good. So like I've done tons of reporting on various discoveries in space astronomy. And I think about a lot of the premature announcements of the detection of life, or even of conditions for life, or all of that. And it feels like it is this sort of thing that haunts the astrobiology community, the exoplanetary community, that you think about the Viking experiment, you think about the Allen Hills meteorite, you think about the discovery of phosphine on Venus. Like I could just go on. And there was a really excited announcement, and everyone was breathlessly excited about this. And then more sober conversations were had, and we sort of reached a level of understanding about where things were. And it feels to me like the exoplanetary community is deeply aware of how this conversation can get off the rails if it isn't approached very carefully. Is that like a sense in the community?
I would agree with that understanding. Yeah.
Yeah. Okay. All right. That's good enough. All right. Well, I want to talk
I'm
about the
happy to
roadmap
build upon
then.
that, though. You tell me.
Well, no. I mean, I think that's it. I mean, I think people really want the answer to this question. Like, did you find an atmosphere on TRAPPIST-1? Is there life there? Mm-hmm. And I think the fact that the answer is taking so long is because people are trying to be really careful about the answer that they give. That's the impression that I get. And that you don't want the quick answer. The people want this answer. You don't want the quick answer. You want the right answer. And sometimes the right answer is going to take longer.
And that's, I mean, even if we were to take the optimal road, like the one we crafted in the roadmap, it's still, it would still be a good 5 years away.
So describe the roadmap. Like, what is the plan?
Yeah, so the plan is, let's say we have a planetary system like TRAPPIST-1, like multiple planets around an M dwarf, and that's how we expect them to be, like peas in a pod, right? And it's really only terrestrial planets around M dwarf that we can use to search for signs of habitability. Well, first atmosphere and then habitability or inhabitability. So for sure, that's what we're talking about. So imagine we find a system like TRAPPIST-1, or say TRAPPIST-1. First thing we want to do is to assess the extent to which the inner planets are warm enough so that we can use emission spectroscopy to assess the presence of an atmosphere. Two options, right, for these inner planets. Either they have an atmosphere via emission spectroscopy, or it's inconclusive or not, really. So if they have an atmosphere, then it's bingo, right? If the inner planet of a system like that have atmosphere, very likely the other ones have too. So that becomes a high priority target, right? And then we can start diving in and we move towards characterization. If they don't, what we've been pitching for, and we're implementing that now. Actually, we just implemented that on July 9th for double transits. What we can do is we can use one of these planets that we know to not have an atmosphere and catch multi-transit event. So that when that planet that doesn't have an atmosphere transit, all the spectral information that we have in transit is actually the information we're seeking. It's the information about stellar contamination. And so we can use that as an anchor to then correct for whatever is going on in the transit of the planet for which we're searching for atmosphere. And we can use that to correct for the stellar effect. That makes sense? So that's one of the other techniques I was mentioning before. Before I talked about the rotation of the star to try to understand the star better. But what we can do, we can catch windows where we have back-to-back transits with the transits of a planet that we know not to have an atmosphere. And we can use that then to correct for stellar contamination. And the cool thing about planets around M dwarf is that they're on very, very short period. And so back-to-back transits happens frequently. Believe it or not, in TRAPPIST-1, I talked about this 5-hour window to get a transit, right? And to get some baseline. Well, 46%, about, one transit out of two happen within 5 hours of another transit. So if instead of targeting small windows and having small programs, we do big programs and we really target these back-to-back transit window, we get 2 transits for the price of 1. And on top of having 2 transits for the price of 1, we actually have information to correct for stellar contamination. So with that approach, what we can do, we can get to step 2, which is doing transmission spectroscopy. And for each of the planets in the system, assess if yes or no they have an atmosphere. Right? And this typically for M dwarf planet takes about 10 transits, give or take. Like 10, 20, but that order of magnitude, 10-ish transits. So that means that if we were to spend, if we invest that time well, the 10 transits is smaller on average because we can get these back-to-back transits and you don't have to spend 10 transits on each planet individually, of course, right? You can have this, there are some windows where you can have 5 transits back-to-back in a matter of 10 hours for TRAPPIST-1, just so we're clear. So in some instances, it's all right. So once we've done that, we reach a step where we can say, is there an atmosphere that's worth looking at? It doesn't mean that for sure we'll be able to assess with 10 transit the presence of any atmosphere, but for some atmosphere, they might be so thin or so challenging to detect in transmission that it's not worth going down the rabbit hole of investing 100 transit to search for key atmospheric signature. Right, it's more like just wait for the next generation of telescope. You've done good enough. But if you find some of these signals, then it's definitely worth spending hundreds of transit to get to in-depth atmospheric characterization. And that's when you can start finding signs of habitability or signs of inhabitability. But getting to 100 transit on TRAPPIST-1 planets will take quite a few years if we really just invest on getting those. But it will be worth it. So that's the high-level view of what the roadmap will be about.
How much time is 100 transits?
Yeah, 100 transits will be, give or take 500 hours.
Right. So a big chunk of time. Yeah.
But is it?
And I understand 1/4 of James Webb's goals, to answer the most fundamental questions that humanity has ever asked. Is that doesn't seem like a big ask.
So actually, it would not even be that, right? If I'm not mistaken, and we can correct the number once we do the edits, I think it's typically of the order of 5,000 to 6,000 hours allocated per cycle, right? So if you do these 500 hours over the course of, it's probably spread over 5 years. It's basically a 10%. Well, no, it's not even a 10% ask. It's a 2% ask.
Mm-hmm. Yeah.
Right. So it's not much.
Yeah. No, and I'm sure if I had the entire astronomical community here in the room with me, we could have a very spirited debate about how to allocate time on James Webb to all the different priorities that have been assigned to this telescope. I mean, it's just it's so precious right now. Every moment that it gets used. And
now here is a real challenge that we're facing. We've not talked about this yet. Is that unfortunately part of the community early on has been convinced, not even no room for doubt and discussions about this, that planets around M dwarf just don't have atmospheres because they are very active early on, and so forth and so forth and so forth. Mm-hmm. And that is part of the challenge. If some people get convinced without room for investigation, then it can be challenging to convince the community to allocate towards such a goal an important amount of time.
But that's a relatively straightforward question to answer once and for all. I mean, get the null result. Like if it is null result, that's important, and we should get it so that we can move on to the next plan. But because these are the easier planets to observe, and so if we can, and they do have atmospheres, and we can detect potential biosignatures, it makes sense to linger on them for as long as is required. So
and still
that seems like the rational approach.
We are in cycle 3, and there is no plan to have this consistent look at the TRAPPIST-1 system.
But now there's a roadmap, so it should be clarified. You talk about TRAPPIST as this unicorn in our discoveries of exoplanetary systems. Is there really nothing that is as good as TRAPPIST?
For terrestrial temperate planet, no. Not for now. Now there are missions, and that's some of the thing we contribute to, that are aiming to find other planets like it. So TRAPPIST-1 was found with a prototype telescope called TRAPPIST. Right, and then out of that success, another consortium with another Belgian name was founded, the Speculoos consortium. So TRAPPIST for the beer, Speculoos for the cookie, and the goal was for TRAPPIST to look at 50 stars like TRAPPIST-1 and search for planets, and TRAPPIST-1 emerged. Speculoos is doing that for 1,000 stars, 1,000 ultra cool dwarf stars.
Right, but so far Speculoos hasn't found another one yet.
No, and it is by far, when you think of signal amplitude, but also signal to noise ratio, so the certainty of the information that you get, it is by far much better than any system in that size regime. And again, I would refer to Figure 1 in the roadmap that really highlight that well. Like if you plot all of the planet known in that regime, what you'll see, and you will really see diagonal in that plot that shows temperature of the planet versus the signal that you can expect, and you'll see late M dwarf, and at the top really just TRAPPIST-1 as the best system for which you can study terrestrial planet in the temperate regime. And then as you go further down and further down, you see that you just look at different stellar type, because it's really the stellar type that define the planet to star area ratio, and the information content directly scale as the planet to star size ratio, area ratios. So only the smallest of the smallest stars allow you to study these terrestrial planets. That's it. And TRAPPIST-1 is the only one known in that regime.
Wow. And I know that there was a paper that we published on about 6 months ago, and someone had done some atmospheric modeling of the rest of the TRAPPIST-1 1 planets. And although the first 2 probably receive too much radiation, the chances of an atmosphere get pretty good as you get farther away from the star. So what are you expecting to see in terms of atmosphere based on the models that you've seen?
I don't expect anything. Remember what we're talking about?
Yeah,
That's the thing. I mean,
yeah.
I just want to be, my stand on this is just same as for the stellar models, right? We can put like millions into upgrading our stellar models. We also need ground truth in order to ground these models into truth. And so we can have this super complex, geophysical models for these terrestrial planets around stars completely different from ours, formation process completely different from ours, amount of volatile completely different from what we can expect here. Age, it's an 8 billion years old system, much older than ours. So with all of these very different from our statements, I just want to keep an open mind, and we can get the data. So I would rather be just, let's get the data and then let's talk.
Yeah. I mean, I think if it does come back airless, if all of the worlds come back airless, and if other M dwarf planets that are observed also come back airless, what do you think that says?
Then it
Keep
provides.
looking?
No, I mean, I think this is where we pause, because one of the things we're interested in one of the question we're interested in answering with this system is, first, let's acknowledge that the Milky Way, the planetary stellar population of the stellar population of the Milky Way is dominated by these M dwarfs, right? And we know that these M dwarfs can produce planets, and quite a few planets in some instances. So what it means is that the terrestrial planet population of our own galaxy is by far planets like the TRAPPIST-1, more so than the one that we find in our own solar system, which begs the question, are all of these planets airless rock or habitable oases? And so if you have a large enough sample, not just around TRAPPIST-1, but other stars like it, maybe more or less active. So we have an understanding of how activity level, flaring, spottedness, and so forth may affect the capability of a planet to replenish a secondary atmosphere. If we have done enough of that sampling, at some point we can come to a conclusion. But we need to do that sampling. We cannot rely on models to drive this understanding.
And they are vastly easier to observe than Earth-like worlds around more sun-like stars.
It's simple.
So
with current technology,
fruit.
It's not even that they are easy. With current technology, they are the only one we can actually hope to study.
I mean, TRAPPIST is lined up nicely between the planets and are lined up in front, so they transit in front of the star from our perspective. And there must be other interesting systems out there, just not lined up perfectly. So, what future methods of that, we talked about that chain you talked about before, like the detection method. What other methods of detection are you excited about as sort of future, as next generation ways of finding more planets?
Yeah, I mean, the next generation really will be direct imaging. And maybe if I can go back on the discussion about habitability, of course there are systems that are of interest for astrobiology with James Webb that would be more with super Earth, right? Like right now the focus was on terrestrial planets, but there are systems with stars that can be a bit bigger, like we were talking about the planet to star ratio. If we are comfortable talking about searching for signs of habitability or inhabitability around planets that are super Earth, so we don't really know if they can, be habitable like the Earth is, because we really have only one sample and it happened to be an Earth-sized planet. Then we can go to system around slightly bigger star, right? And that opened the door to discussions of other planetary systems. So that depends if you want to go there or not. But there is room to do what we're talking about for other stellar types. And they come with their own challenges, right? There'll be less stellar contamination in some instances. There might be more stellar activity, but there is room to do something there. But if we really move further down and we look at the next missions, it will be, or the next technique that will really help us do this at a population level, because we won't be limited, you're right, by geometry, having the planet needing to transit. Then we're looking for direct imaging. But direct imaging is going to be a challenge for these M dwarf systems, right? Because as we just talked about, these planets are very close to their star. because the star is very, very, very faint. So for the planet to be habitable, they need to be quite close to the star to have enough flux coming from the planet, from the star. So that means that they are really compact, right? The 7 planets of TRAPPIST-1, they are, if I'm not wrong, 8 times, the furthest away is 8 times closer to TRAPPIST-1 than Mercury is to the sun. That's how packed the system is, right? And if you think of all, and I'm sure your audience is used to seeing these detection charts, if we were to do direct imaging, we will find the Jupiter, the Saturns in a sunlight in a system like ours. But finding the Earth, the Mars will be a challenge. Venus, maybe if it's bright enough. So things that are even closer to the star, forget about it. So direct imaging will be great for analog to our system. But for systems that are M-dwarf system, it will still be a challenge in most instances. So whatever we do, that might be the path forward, even when we start doing direct imaging, transit spectroscopy for these M-dwarf systems.
But you say like finding worlds like the Earth, like it's a bad thing. Like,
no. Did I say that?
No. But that's my joke here. Is that I think that the direct imaging technique will be a lot more effective for finding worlds like Earth, worlds like Jupiter, finding things that are a lot more analogous to our own solar system. Like we have this really distorted perspective of what exoplanets are like compared to the sun, because all that's been found is the low-hanging fruit, the stuff that is enormously hot and orbiting around its star at a fraction of the distance of Mercury, because it makes lots of transits. And then the things orbiting around M dwarfs, because the difference between the brightness of the star and the planet are very similar. But I think this is what has to be observed, because this is what's the easiest to observe. We're pushing the limits of our current technology. So I want to go back to direct imaging. Like, what is the pathway forward with direct imaging that gets us a more reasonable understanding of what's in a planetary system?
Well, so, okay, you're right that there's observational bias all over the place, right? And as we move to the next generation of technology, we keep on widening the parameter space that we can explore. And direct imaging would really provide a huge step forward from that perspective. So I do think that, I can't say what will be next. It will just be getting closer and closer and closer to the star. So we'll be resolving more and more of that.
But that's bigger and bigger telescope then. Right? Is that it? It's bigger and bigger in telescope, or interferometer, or a Knowling interferometer, or whatever.
Baseline.
Right? Like some
baseline. Yeah, that's it.
A larger baseline.
And that's it. What's next? If you
and then
think
viewing
about,
in infrared.
Yes. Yeah, because that's where most of the spectral information is for the planets. For molecules, this is where they are most present. And then there's emission as well. If you want to see them further away, there's a combination of the two.
Right, and the distinction in the brightness of a planet and its star is easier to resolve in infrared compared to visible light, for example.
Exactly. So this is where we're going. Well, one of the challenges with direct imaging is that in terms of design, as a community, we'd have to ask ourselves: are we going to try to fly single aperture instruments that have tens of meters in aperture, or are we trying to move towards a design with fleets of meter-sized telescopes? But this is really the path forward for. But now we're talking of like 20 plus years down the road.
I don't mind.
Okay.
What is it? Well, what does it look like? What do you think that? Because if this is the goal of humanity, to understand our place in the Milky Way, to understand our place in the cosmos, it's a worthy goal. So, what does the instrument that gives us the answer look like? Do you think the one that images worlds or images other stars, picks out the planets, provides promising candidates to other scopes for more detailed observations, like the habitable world? Like, what is the Kepler or TESS of direct imaging?
Yeah, you see, you're putting me on the spot here. I don't know yet if the habitable world observatory is the optimal design for that. Like something that maybe was exploring, and I won't go into detail, but a project like Nautilus. Have you heard of Nautilus?
Mm-hmm.
You have?
Yep.
Okay.
Mm-hmm.
Yeah. So designs that are, more transformative from that point of view than HWO can be, simply because of the limit on the aperture.
Yeah, sorry, I just want to make that distinction, right? Like the Habitable Worlds Observatory is the Corot of like once the planets have been found by Kepler and TESS, then you bring on something like the Habitable Worlds Observatory to make observations on a couple of worlds that are the best candidates, the ones that you can really get that spectroscopic data on the atmospheres. But I think about just the finding, just the knowing our place in the cosmos,
the
how
detection.
many of these stars,
what is sheer
right?
detection.
The detection, as opposed to the characterization, right? What is because I was going to ask you about the characterization, but first I just want to talk about detection.
But I think it's the same instrument. I do think that fundamentally we're looking at the same instrument, right? Which mission would you use? So the analogy that you make is great, and at the same time, the detection mission that you mentioned are our transit mission, right?
Mm-hmm.
And so
no, I want a direct imaging mission.
Exactly, but the thing is, if you do a design for a direct imaging mission, you do a design that's your design is already half the way to something that's also good for characterization. So why do two separate things? And so that was the answer to the question. I think you package that as one thing.
Okay, so convince me of that.
I think I just did. Why do two separate things?
No, but like why? I guess why is the detection? Why is there TESS and Corot? Why is there TESS and Ariel? Right? Like why are there two different missions? One is great at staring at a big chunk of the sky and finding all of the ones that have interesting planets orbiting around them, and another one is used to make very detailed observations on the known planets to learn more about them. Why? When it comes to direct imaging, why do those become the same mission again?
Yeah, so this is where I'm stepping out of my area of expertise. So I would take everything I say for your audience with a grain of salt.
Totally. Yep. Everyone listening, everyone, the press people at MIT. Yep. This is nonsense. This is we've just cracked open a Trappist beer in front of us and a bunch of speculous crackers, and we are now having just a free-floating conversation here. Yeah.
So in order to do direct imaging, you're going to have these large collecting area. And so just to resolve the planets away from its star, you're going to need to have a significant collecting area, which is different from what you're looking at when you do transits. Think about the aperture of TESS, right? These are 10 centimeter in aperture, and that's enough to see the star being masked. So what you're looking for is an effect on something bright when you do transmission or transit detection. When you do direct imaging, you're looking for the flux from the planet, which in and of itself is very tiny. But on top of that, you need to have an aperture that's big enough to collect that tiny amount of flux and disentangle from the star. But also, and most importantly, you need to have it big enough so that you have the spatial resolution to start hoping to be able to mask the thing that's next to it that's a billion times brighter. Depending on the planet you're looking at, but I think that's significantly brighter next to it, the star. So just out of sheer design necessity, your detection technique is already requiring you to have this large aperture. So this is usually the requirement to move towards characterization. So I think out of sheer necessity, you already have a design that isn't that far from what you need later to do characterization. So that's how I would think of it.
Right. But when I think about an analogy of, say, Kepler, like with Kepler, it was staring at this one spot in the sky. And of course, its reaction wheels failed and they had to change the mission. But they were staring rock solid at this vast field, picking out all of the changes in brightness across all the stars that are happening. But obviously, if you're going for direct imaging, that's not going to work. Because you've got all these stars. So you somehow need to have coronagraphs across all of the stars in your field of view, and so that you can pick out the planets.
Okay.
Is that correct?
That is
impossible?
Correct.
I guess. And so, is anybody thinking about this? Is this impossible?
I think a lot of people are thinking about this. Yeah.
Yeah. Okay.
So I don't
All
think it's
right.
impossible. No. I do think that
Okay.
there's a good understanding that this is where we have to go. As you
Yeah.
correctly highlighted, the approach that we currently use is based on our technology, which induce limitation, and so we're going for transiting system, which is great because again, we need to have the community moving. But ultimately, what we need to do is direct imaging because most of the
Yeah.
systems are not transiting. So we know we have to go there. So we will have to design the technologies that answer that problem. So we will get to that
Yeah.
place.
And I think when you think about, say, the ground-based telescopes, like the extremely large telescope that's in development, you think about the Habitable World Observatory. These are, they will be able to look one star at a time, carefully mask the light from the star, attempt to see the planets orbiting around it, and so then I guess I'm kind of leapfrogging to what comes after that, right? So I understand that it's a fairly large
And
speculation, but
let's
um,
the good thing is also it's worth highlighting because it seems overwhelming to think that you can only do one system at a time in comparison to Kepler that was just staring, right? But the difference is that you just need snapshots for the detection, right? Like TESS, Kepler, they have to stare and just wait for a transit to happen. For direct imaging, you take snapshots and then you see if there are some point source and how they've moved, and then you can derive the orbits. So you can go from one star into the next, and you can do many of them overnight if it's ground-based, or many of them over the course of a day. So I think that's an important distinction to make, which also goes back to what we're talking about with regard to collecting area, right? You could afford to go to a small aperture with TESS because you're staring, and so you can bin on big amount of time to collect photons. But there is a big aperture that you can then use for characterization. You can just take snapshots and then see if something comes up. And then if something comes up, you can use your big aperture and do a stare to gather the data. So it's a
got it. I understand it. So you're like, again, back to the astrophotography. Like, I can take a 5-second exposure of Andromeda and I can detect the presence of Andromeda, or I can do a 12-hour stacked exposures of Andromeda and see all of the dust lanes and all of that by just coming back with the same instrument and just collecting more photons. Okay, I understand now. I'm convinced. Julien, what are you obsessed with?
what I'm obsessed with. I'm really obsessed with how much we can learn about ourselves by looking for planets around other stars. That's really the reason why I moved to this field. So by training, I'm an engineer in aeronautic and aerospace, and at some point I drifted away from planes and rockets and satellites because actually that's when I came to MIT first. Sarah Seeger introduced me to the prospect that at some point we may find terrestrial planets, and we may be thinking of searching for signs of atmosphere and so forth around them. And I got convinced by the fact and excited by the fact that I just feel like so much is happening to humanity right now. If we get to a point where we can have this profound paradigm shifting experience, really help people embrace that we're really on our space odyssey, then it's totally worth it. So that's what I'm excited about, because I feel like I started this journey now 14 years ago, and I feel like with just a few years, within the decade that's coming, we're going to have incredible experiences coming from astronomy. And you've seen the news related to Mars recently, right? They don't say what's going on with Perseverance. They don't make the statement that something has been found, but there's something really exciting happening there. So I feel like both in the solar system and outside of the solar system, a lot is happening, which is good considering everything that's happening on Earth. So that's what I'm excited about.
Yeah, it's amazing how many separate pathways are being explored simultaneously. Whether it's, Sarah Seeger's involved in this mission to Venus to explore the atmosphere of Venus, and then there's the work that's being done by SETI, and then there's the work that's being done on the surface of Mars, and then the Europa Clipper is preparing for launch to look for plumes at Europa, and people are making better observations of Enceladus, and of course, there's the work be done with James Webb. Yeah, I could probably list out 20 different paths that people are searching for signs of life out in the universe. And that really feels transformational, that 20 years ago, it was something you didn't talk about. And there was no funding made available to the astrobiologists and SETI and any of this kind of stuff. And now suddenly, not suddenly, slowly, inexorably, it's always been a scientific question all along. And And now the funding and the effort and the respect is being delivered to the community to try to get an answer to what is possibly the most profound question humanity has ever asked: is, are we alone in the universe?
Exactly. And I feel like it's coming, it's very timely at a time in history where a lot of challenging are emerging. And I'm not going to talk about geopolitics, but I'm just going to talk about, say, AI, right? AI coming in, and that is going to transform, disrupt the job market, say, right? And in economies where people have developed a sense of self and a sense of values that's directly tied to their job, coming to a place where we can have at the same time answer to these profound questions. Are we alone in the universe? What does it mean to be a sentient being, the dominant sentient being on this planet? I think these things are just going to have an interesting and long-lasting effect on our society. So that's really what I'm excited about.
I would ask you which of those pathways you think is going to bear fruit first, but I'm assuming just by the career as an aerospace engineer working in exoplanetary science, you've sort of chosen you've placed your bet.
Wow, that's I would not say that. I would not say that. Yeah, I do think that in terms of life elsewhere in the solar system, we have much higher chances. But I think that each are going to have their very different impact on our societies. Very unlikely that we find sentient beings in our solar system. I'm going to say very unlikely, but I'm not going to put bets on that. And so I would say a lot of people are not necessarily going to resonate with, or as much with, the fact that, say, we find microbial life on Mars, for example. Right, like it's going to have an impact, especially if we start connecting that to our own tree of life. It's going to have an impact. I'm not denying that, but it seems to me that intelligent life is probably what people are going to click with more so than just microbial life, and that's most likely going to be related to findings outside the solar system. Yes.
Yeah. But then, for example, James Webb able to detect the presence of chlorofluorocarbons in the atmosphere of TRAPPIST-1, like that would tell us.
I mean, that's a cool thing with technosignature. Technosignature, it's very unlikely there's a false positive, right? I mean, if you think of how life evolved, life basically does advanced chemistry, but it's still geochemistry, which is why it's difficult to say, is it life, or it's a weird chemical process that we don't know yet. But if you have a technosignature like CFCs and so forth, right, it's easier to detect intelligent life than it is in some instances to detect just life.
Yeah, absolutely fascinating. It's an exciting time. One way or the other, we will know an answer in our lifetimes, whether there is life or in an increasing bubble around us, there's no life. And both are, in the words of Arthur C. Clarke, equally horrifying. So I think it's a fascinating time to be watching this journey unfold, and to not know the answer is exciting to me, because I want to find out the answer. It's like watching a big game, and we're right at that last moment of seeing who's going to win or lose.
So we have to stay healthy, and we have to take care of ourselves so we can just, live to that point.
Yeah, exactly. Well, Julien, thank you so much for your time, and good luck with finding atmospheres on the TRAPPIST-1 planets.
My pleasure. Thanks for having me.
I hope you enjoyed that conversation with Julien de Wit. I'm going to talk about some of my thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Bill, David Giltonen, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modso, Paul Robach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. This interview really filled in some missing pieces in my understanding and knowledge about the state of observing planets around red dwarf stars. Why haven't we found out any information about the TRAPPIST-1 system from the observations of James Webb? And, it really is about getting a good answer, not the quick answer. And I think the answer we want is, well, did you find atmospheres or not? Well, the results are inconclusive. That doing the kinds of observations that it's going to take to get a good answer is going to take more time, and that's going to take more study. It's going to take more time dealing with the data, and it's going to require making sure that you've got the right answer and not just the quick answer that's then going to lead to arguments, the kinds of things we see over like the Viking experiments, which were inconclusive and people have been arguing about them for decades. And so I think we know better now. We know that if something really interesting has been found, you've got to be sure and you've got to be able to back it up with really high confidence data. And this is the roadmap. This is the plan. So we've got to be patient. I can be patient. I hope you can too. All right. I hope you enjoyed this conversation, and we'll see you next time.